1a.Charles Steinmetz. 4 lectures on relativity and space. 1923. All books on my channel are in public domain. Please subscribe. If you like it, please give thumbs up, share and comment. 4 lectures on relativity and space. Preface. The theory of relativity developed by Einstein and his collaborators is the greatest scientific achievement of our age. The layman is therefore fully justified in wishing and asking to know what it is about, and in his desire to get at least a glimpse of the new and broader conception of the universe and its laws which this theory is giving us, and to understand what fundamental revolution in our scientific world conception it is causing in bringing order and system out of the previous chaotic state. Unfortunately, the relativity theory is intrinsically mathematical, and it is impossible to give a rigidly correct and complete exposition of it without the extensive use of mathematics. The best that can be done, therefore, in explaining the theory of relativity to the layman, and to the engineer who is not an expert mathematician, is to give by analogy, example and comparison a general conception of the theory and its fascinating deductions and conclusions. Such a conception must inevitably be approximate only and cannot be rigidly correct. This must become evident to the mathematical physicist. However, it is the best that can be done, and I believe it is sufficient to justify fully the little effort required from the layman to follow the exposition. After all, the non-mathematician is not interested in rigidly following the intricacies of the mathematical reasoning involved. Rather, it is his desire to get a general knowledge and understanding of the new ideas on time and space, on the laws of nature and the characteristics of our universe, which the relativity theory has deduced, and of the wonderful researches into the nature of space which nearly a century ago were carried out by the great mathematicians and have now at length become of physical significance and indeed been the mathematical foundation on which the theory is built. It is from this viewpoint that the 4 following lectures have been edited in order to adapt the expositions to the non-mathematical mind, even when thereby some accuracy had to be sacrificed. The first lecture was given before the Layman's League of the Unitarian Church of Schenectady and repeated before the Pittsfield section of the American Institute of Electrical Engineers. The other 3 lectures, which go more deeply into the conclusions and deductions, and in the last lecture into the geometry of space, were also given before the Pittsfield section of the Institute. In conformity with the general attitude above explained, which I consider necessary to make the subject intelligible to as large a circle of readers as possible, I have introduced the constancy of the velocity of light as an axiom rather than by Michelson's experiment, and have referred to the latter only as corroboration, for the reason that in my opinion the non-technical man in search of knowledge prefers to be told the conclusions descriptively rather than to read through the record of the experimental deductions. The derivation of Einstein's law of gravitation from the inertial motion in an accelerated system is explained by example and shown as a mathematical transformation. This gives to the layman a general understanding of the principle, but is not rigidly correct, as it gives the impression that the derivation involves no arbitrary assumptions. However, an attempt to explain general coordinates to non-technical hearers did not appear to me to be justified. And in the last lecture I tried to explain the assumptions involved in connection with the metric axiom. Similar approximations and deviations from mathematical rigidity are found in the discussion of the imaginary unit as a quadrature vector, in relation to Minkowski's space, in the comparison of gravitational and centrifugal force, in the relation of acceleration and velocity in the derivation of the space curvature in the gravitational field, and in the explanation of the curvature of 3 space by analogy with that of 2 space, which obviously is limited by the conditions of the former being more complex. In a number of other places, too, the mathematical physicist will find statements and deductions which are not strictly exact, but which appear to me justified since they appeared the only way of giving an approximate conception of a mathematical subject without mathematics. In general, I have preferred the synthetic method to the analytic as more intelligible to the non-mathematician. While most mathematicians are more familiar with the analytic method and consider it a more powerful tool, the synthetic method has in the hands of a man like Steiner proven fully as powerful as the analytic, and it has the advantage that we see what we are doing and get a physical conception of it. Thus the general or non-metric geometry is exemplified by the collinearity between the plane of points and the bundle of rays. The metric axiom is discussed, the analytical analogy of which will be obvious to the mathematicians, etc. The entire 4th lecture has been devoted to the conception of mathematical space, its curvature, etc. This is one of the most fascinating subjects of human knowledge, and the fundamental importance which through the relativity theory it has assumed in the realm of physics makes a general understanding of it desirable for the layman. The more so as some of its conclusions, as to the finite size of the universe, etc., have an interest reaching far beyond mathematics and physics into the realm of philosophy and beyond. Charles Steinmetz. Schenectady, New York, December, 1922. 4 lectures on relativity and space. Lecture 1. General. A or relativity of motion, location, and time. The theory of relativity as developed by Einstein and his collaborators has revolutionized science by sweeping aside many of the limitations which hitherto fettered the human intellect. But, being essentially mathematical, a general conception of it can be given to the non-mathematician only by the use of analogies and illustrations. And this inevitably involves a certain looseness of argumentation. The following pages therefore may serve to give a general idea of the theory of relativity and its consequences, but not to review it critically. The theory of relativity starts from two premises. 1. All phenomena of space, time and motion are relative. That is, there is no absolute, motion, etc., but motion, location and time have a meaning only relative to some other location, time, etc. 2. The laws of nature are universal. That is, they apply in the same form everywhere, whether in a speeding railway train on Earth or in the empty space between the fixed stars. So far, these two premises appear simple and rather obvious, but startling and revolutionary ideas appear when carrying the reasoning from these premises to their ultimate conclusions. As Einstein has done. Suppose, for instance, you happen to run your car at 30 miles per hour against a stone wall. There seems nothing relative about this. The wreck is very real. The stone wall does not budge, and when a rapidly moving mass meets an immovable body, mechanical energy is set free destructively. But is the stone wall really immovable? Is it not a part of the Earth, which spins around its axis at 800 miles per hour so that both the stone wall and your car were moving? And perhaps if you happen to drive the car in a westward direction, that is, against the rotation of the Earth, your car really was moving more slowly than the stone wall, was going only 770 miles per hour, and the stone wall 800. But think further. Is not the stone wall, as a part of the Earth, revolving around the Sun at 70,000 miles per hour, and is not the Sun, and with it the Earth, and the stone wall, and your car, also moving on an unknown path among the fixed stars? So that really you know nothing and can know nothing about the actual or absolute speed of the car. All you know is that the relative speed of the car, that is, the speed relative to the Earth and thus to the stone wall, was 30 miles per hour. But that is sufficient to let you understand the effects of the car meeting the stone wall. So with location. The room in which you are sitting while reading appears fixed and definite. But the only way you can describe its location is by referring it to some other body or location as reference point, by saying, for instance, that your room is located X feet north and Y feet west and Z feet above the Surveyor's Markstone on City Hall Square. Or you can give its latitude, longitude, and altitude, stating that from the starting point of latitude, longitude, and altitude, that is, where the equator meets the zero meridian at ocean level, you go so many degrees north or south, then so many degrees west or east, and then so many feet up or down, and thereby reach your room. 3 distances thus are required, measured in 3 chosen directions, from a chosen starting point, to locate a point or an object in space, and therefore we say that space has 3 dimensions. But do these 3 distances really locate you in your room? Suppose somebody, reading the directions, should try to locate your room 1,000 years hence. He would not find it. Thus one more thing must be given, the time, measured from some arbitrary starting point, for instance, Anno Domini. Thus, you see, to locate anything in this world of ours requires 4 measurements, 3 distances, and 1 time. And we thus can say that the world and its events have 4 dimensions, 3 dimensions of space and 1 of time. But all such location of events in the 4-dimensional world can only be relative to the arbitrarily chosen reference points in space and time. In bygone ages, when people thought the Earth flat and immovable as the center of the universe, they could dream of referring location to an absolute stationary reference point. Say the capital of Rome. But when we learned that the Earth is a sphere, spinning around its axis and revolving around the Sun, the Earth ceased to offer any fixed and permanent reference point in space. The Sun then was chosen. But the astronomers found that the Sun also is moving among the fixed stars. And the fixed stars do not stand still, but are moving every which way, so that all the attempts to find something immovable and fixed in the universe have failed, and thus all motion, all location, can be relative only to other objects, which are also moving. Be an effect of relative motion on length and time. Suppose you toss a stone across your room. Observing the point at which the stone leaves your hand, the direction in which it leaves, and the speed. The physicists can calculate the path of the stone as it curves downward and finally comes to rest on the floor of the room. Suppose now you are on a railway train, moving at constant speed on a straight, level track, and toss a stone across the car in which you are riding. From the same 3 observations, the point in the moving railway car where the stone leaves your hand, the direction, and the speed relative to the car at which the stone leaves, the physicist by the same laws calculates the path which the tossed stone traverses in the car. Whether the car is moving at constant speed on a straight, level track or standing still makes no difference. The path of the stone is the same, as the same laws of nature apply everywhere. If the laws of nature are the same in the railway train moving at constant speed on straight, level track as they are on the rigid platform of the Earth or in the empty space among the fixed stars, then the speed of light must also be the same, 186,000 miles per second, and so must be the speed with which the electric current travels in its circuit, which is the speed of light. This is important because all observations depend on it. Any event is either observed by seeing it or recorded by some electrical arrangement. And in either case we do not get the exact time when the event occurs but a time later by the time it takes the light to reach our eye or the electric current to flow from the event to the recording device, and to get the exact time of the event, we therefore have to allow for the time taken by the light or the electric current. Owing to the enormous speed of the light, this time difference between the moment when the event occurs and the moment when we observe or record it usually is so extremely small as to be negligible. But not always. For instance, when on shipboard out on the ocean the chronometer has stopped and the mariner tries to find the location of his ship from the stars. He might use the eclipses of the moons of Jupiter for this purpose. But when he sees the eclipse it has already passed by from 30 to 50 minutes, depending on the relative position of the Earth and Jupiter, owing to the time which it takes the light to go from Jupiter to the Earth over the hundreds of millions of miles of distance. But if the speed of light in the moving train must be the same as on the stationary track, we get some rather strange conclusions. Suppose we place a lamp on the track, back of the receding train, so that the light shines along the track, for instance, a signal light. The beam of light travels along the track at 186,000 miles per second. The train moves along the track, in the same direction, at 100 feet per second. Therefore, relative to the train, we should expect the beam of light to travel at 186,000 miles less 100 feet per second. It would be thus with a rifle bullet. If I shoot a rifle along the track at the receding train, and the rifle bullet travels along the track at 2,000 feet per second, while the train travels in the same direction at 100 feet per second, then the rifle bullet will catch up with the train and pass through the train at the relative speed of 2,000 less 100, or 1,900, feet per second. But the constancy of the laws of nature teaches us that if the beam of light travels along the track at 186,000 miles per second, and the train in the same direction at 100 feet per second, the speed of the beam of light measured in the train, that is, its relative speed to the moving train, cannot be 186,000 miles less 100 feet, as we would expect, but must be 186,000 miles per second. The same as its relative speed to the track. Now, the only way we can explain this contradiction is to say that when we measured the speed of light on the train our measuring rods were shorter, or, using the length of the train as measure, the train was shorter, or the time was slower, or both. These three possibilities really are one. It can be shown that if the length of the train is shorter, the time must be slower in the same proportion. Thus this leads to the strange conclusions that, when the train is moving, to the beam of light coming from the outside, and to an outside observer, the length of the train has shortened and the time in the train has slowed down. But if we now stop the train and remeasure it, we find the same length and the same time as before. This conclusion from the two premises of the theory of relativity is so against our accustomed ideas that we would be inclined to reject it if it could not be verified by experiment. And the experiment has been made repeatedly. It is true a difference of 100 feet per second out of 186,000 miles per second is so extremely small that it could not be measured. But we can speed up the train and, instead of 100 feet per second, run it at 100,000 feet, or 20 miles, per second. We have such a train. The Earth on its path around the Sun moves about 20 miles per second, and the speed of light going with the motion of the Earth then should be 20 miles less. Going against the motion of the Earth 20 miles greater. But the experiment shows that it is the same. An experiment has proven this with an accuracy many times greater than the difference in the speed of light which we should expect but do not find. So that the fact of the constancy of the speed of light is beyond question. Beyond question, then, also, is it that for an outside observer motion shortens the length and slows down the time on the moving body. But not for an observer moving with the train, for him length and time are the same. See